السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. Last time we started to talk about local search, and we said that it's different from the search algorithms that we talked about before, in the sense that we have only one state that we are exploring, and that state is complete configuration. And we try to move from that state to another local state that is better than it. And we started with hill climbing algorithm. In hill climbing, as we mentioned last time, we can get to a local maximum because we always try to find in the neighborhood, in the successors in the successor of that current state, we are trying to find a better state. If we couldn't, then we will be done, and it might be a local maximum. And of course, we are trying to reach global maximum. That's the actual solution of the problem. But we might start on local maximum, we might start on a shoulder, or even a plateau. And we solved this quiz together towards the end of last lecture. Today we'll start with a pseudocode, which, as you see, it's very simple. We start with an initial state, and then we loop over this code in which we get a highest value successor of the current. We call that the best neighbor. And if that best neighbor, if the value of that best neighbor is better than the value of the current state, then we will move to it. Okay, so we will assign the neighbor to the current state, and we will continue the loop. If it's less than or equal to the current value, then we will return the current state. Okay, so we will change the current state only if that is not satisfied, which means that the value of the neighbor is greater than the value of the current state. So that's the standard hill climbing algorithm. Now, what happens if I couldn't find a state among the successors that is better than the current state? What if I found that the best state, the best successor, okay, is of equal value to the value of the current state, which is the condition of equal here? If that happens, then I will stop, right? Based on that algorithm, I will stop, which means that this algorithm will halt, will stop, if it reaches a plateau. What is a plateau? This is called a plateau, okay? Because all of the states around me are either worse than me or equal to me. Okay, so there is no better state, so it will stop. Now the question is, can we allow sideways move? Maybe we are actually at a shoulder, so we reached that point. For example, let me change this to a pointer. We reached this state, okay, and based on that algorithm, we will stop because there is no better state. But maybe if we moved around, what we call here sideways, so if we moved to the side here, on the side here, maybe we can reach the global maximum. Maybe that's a shoulder, not a plateau. Okay? So should we allow that, hoping that that will lead us to a global maximum? What do you think? Should we change this algorithm in a way that will allow us to do this sideways? Any ideas? Any thoughts, Mahmoud? Why? Maybe it's a shoulder, as I said, and after some time we might get out of this space, and we might reach the global maximum. So do you agree with me that it might be helpful in some cases? Yeah, Ghanem, I am talking to Mahmoud. You didn't even raise your hand. Okay, so Mahmoud, you are still with me. Do you think that it might be good in some cases? Okay. Yeah, so we need to avoid an infinite loop, because if we allow that forever, we might get into an infinite loop, right? So we need to break this infinite loop. So maybe a good option here is to allow a specific limited number of consecutive sideways moves. And by sideways move, I mean move to a state that is of equal state. If I allow, for example, maximum of 100 consecutive moves like that, and if I couldn't find a better state, then I will stop. If not, then of course I can move to a better state. So with that limitation, that will make the algorithm much better. It can reach better solutions. Okay, and at the same time, it will not stuck forever into a plateau or something like that. So that's an idea that can improve this algorithm. Now, is that algorithm complete or not? Yani looking at this standard algorithm now, is it complete? What do you mean by complete first? Someone else other than Mahmoud. Is it complete? And what do you mean by complete actually in this case? Anyone else? Yusuf? Wa alaikum salam. Very good. Yes, it can. Yes, it can stuck at a local maximum. And if it can stuck at a local maximum, then it's not complete, because the definition of a complete means it's guaranteed to find a solution. And the solution here is a global maximum. Okay, local maximums are not solutions. So if it can stuck, and it might stuck, then it's not complete. Okay, so hill climbing, the standard search algorithm, standard hill climbing algorithm is not complete. How about optimality? Is it optimal? Any thoughts? Saad? Okay. Yes, again, the same reason. Yeah, the same reason. It can stuck at a local maximum, and we can even say it in a simpler way. Since it's not complete, it cannot be optimal, right? And if it's not guaranteed to find a solution, then of course it's not optimal. Okay, because optimal means it will find the optimal solution, but it's not guaranteed even to find a solution. So that's not optimal. Yusuf, you have a question? No, it's the of course it's not. Yes, yes. Okay, one point here that maybe I didn't say it explicitly. We might have multiple global maximum, by the way. All of them are of the same value. All of them are solutions. Okay, so hill climbing is not guaranteed to find any of them. And if that's the case, then of course it's not optimal, because optimal means it will find the best solution. Yeah, yes, it might not find the solution in the first place. Yes. Okay, so if it's not complete and it's not optimal, then what's good about it? Why should we study it? Why should we use it? It's not optimal, it's not complete. So is there any good about this? Mahmoud? Okay, I'm talking about the algorithm that we discussed already now, the standard one. What is good about it, Mahmoud? If any, maybe there's nothing good about it. طيب, I thought Mahmoud is talking to me. Now it seems not. Faisal? Okay, but is that good? No, it will not find multiple global maximum or local maximum. It will find one that might be local maximum at the end. And that's in principle is not good because it's not complete. It's not guaranteed to find the solution. But think about it in the sense that it is a greedy algorithm. We said last time that hill climbing is a greedy algorithm, right? So what is good about any greedy algorithm? Saad? Okay, sorry, Faisal, let me ask Saad. Which means yes. So the time here is the issue, or not the issue. Is the good thing. So it is fast. Okay, as any greedy algorithm, it is fast. Okay, it might not lead to a good solution eventually. It might not lead even to a solution at all, but it is fast. So this is one. Anything else? How about memory? How much memory we need here? Abdurrahman? Okay, it's not about that we don't have lots of computation, Abdurrahman. We might have. Yes, simple also doesn't mean that it needs less memory. Okay, it might be simple but needs a lot of memory. But in this case, you are right that it doesn't need a lot of memory, but not because it's not doing a lot of computations. It's because it. Yes, because what about the fringe here? It's not that there is less nodes in the fringe. There's actually one node in the fringe always, okay, which is the current state. We don't actually keep any fringe. We don't keep any list of potential solutions or potential paths. Okay, so we are always working on one state in this case. So the memory is the needed memory is very small. Okay, so that's another thing that is good about hill climbing. Let's see now an example. We have this 8 queens problem. Again, we are now moving each queen in one column, and we define the value of a state to be the number of pairs of queens that are attacking each other. Okay, so if you check this current state, you will find that H is 17. So in that current state, with the queens in the shown positions, we have 17 pairs of queens that are attacking each other. Okay. Type. Now, what is the next state if we are using the hill climbing algorithm? We should, from that state, we should check all the successors of that state and find the best among them. And then we move to that state. Now, if you look at the board, you will find the numbers. Okay, there are numbers in each position, and that number indicates the value of the state if we moved the queen from the corresponding column to that position. So, for example, if we move that queen to that position, then we will have 16 attacks. The value is 16. So in that position, we will have 16 attacks. If we move that queen to that position, we will have 12 attacks. Okay, so here the successors are the states from the current state by moving one queen only through the column, through its own column. طيب. Now given that definition, where should be the next step? عبد الرحمن? Very good. Why least, not most? Very good. Yes. Yes. So no, here we are not maximizing, we are minimizing the value. Okay. So what should be the next state then? You mean this one? 212. Okay, so here. Okay, so or here, right? Yeah, so since we have multiple states of the same value, which is 12, that's the best. Then yes, you can arbitrarily choose any of them. So that state can be moving the queen, as you said, Abdurrahman. Moving the queen from the second column here to that position will be the next state. Now, do we need, and Abdurrahman is still with me, do we need to change after, let's say that we moved now the queen from that position to that position, do we need to change the numbers around us? The numbers. Yes, exactly. We need to change the values for all the successor states, okay, so that we can select the next state and so on. Okay, so I hope that by now, by this example, the algorithm now is more clear. Now let me ask you about this quick quiz. What is H for this state? Faisal? Okay, so you see that there's no attacks here. Okay, any other answers? So Faisal says H is 0. Any other answers? Any objection to Faisal, Abdurrahman? So what is H then? Where? Can you tell me? Which column? عبد الرحمن، يعني انت هوشتنا وسبتنا يا عبد الرحمن، يعني ضاع عليك. طيب okay, that's fine. Faisal, it seems like he wants to change his mind. Faisal, you saw the attack. Okay, which one? The top. So this one and the fourth row, this one. Okay, yes, they attack each other. Okay, any other attacks? So if that's the case, what is the value of H, Faisal? It's 1. Yeah, I agree with you. Actually, it is 1. Okay, so the value of H here is 1. Okay, طيب. Where is the next state? Can we get rid of this attack and reach a solution from that state? Yani we are very close, right? Yani here, if you remember, we had 17 attacks here with that position, with that state. Okay, now we have 1 attack only. We are very close to a solution. Is there a solution actually from that state? Can we reach a solution? Can we move, in other words, can we move any queen in its column to a position where we will avoid any attacks? Okay, not just to waste time. There's no way to make this solvable from that state. Okay, okay, Mahmoud. The last one. Okay. Here. So move this here. Okay, so yes, that's not a solution, of course, and I'm sure that we cannot find actually a solution. Okay, so we will be stuck. So that's a local maximum. Okay, so let me move this. So this is a local maximum now, and we will not be able, from that state, we will not be able to find the global maximum. Okay. Any question about this? Okay. Now let's move on to variants of hill climbing. The first variant is called stochastic hill climbing. The idea here is that we will choose at random from among the uphill moves. What do we mean by that? In the standard algorithm, we said that if we check the pseudocode, we said that we will get the highest valued successor, which means that among all successors, we will find the best of them, and then we'll move to that best if it's uphill, if it's giving us a value that's better than the current state. That's the standard algorithm. But the stochastic hill climbing, it looks at all successors, it finds among them those that are better than the current state, but it doesn't always choose the best among them. It chooses one of them randomly, but without equal probability for all. Actually, the best one will have higher chance, will have higher probability to be chosen to be the next state. So the probability of choosing any one of the uphill moves depends on how good they are. As the state is much better than the current state, it will have higher probability to be chosen. But still, I might not choose the best next state. Okay, but I will choose one among the uphill moves. Now, the side effect of that is that we will converge slower because we are not always greedy, right? We are not greedy. In greedy, we always take the best local. Okay, but here sometimes we'll take the best, sometimes we'll take not the best, so it's not greedy. So it might be slowly, it might converge slower. But in some state spaces, it might find better solutions. Yani getting into directions that are not greedy locally might lead us eventually to get to better solutions. So that's so the downside is that it's slower, but on the positive side, it might find better solutions. Now, is that complete? Is this variant complete? Is it guaranteed now to find a solution? Yusuf? No, who said that I will choose the highest probability? I said that the probability of selecting it will be higher, but doesn't mean that it will be selected. And even if we selected the best, that will be the standard one, which is incomplete, right? Okay. Okay. No. Okay, let me explain that. Okay. We always consider one state. Okay? But to move to another state, we have to consider its successors, of course, right? So we need to check the successors state from the current state. Okay? Now, among the successors, there are some of them that are better than the current state, and some of them are worse than the current state. Okay? Forget about the worst ones. Let's only consider the ones that are better than me. Me is the current state. Okay? With me, Mahmoud, or who is with me? Yusuf. Okay. So Yusuf, now we look at the ones that are better than me and select one of them randomly. But we will not select uniformly among them. And they will not be all equally probable. The probability of selecting any of them will depend on how good they are. And the best among them will have higher probability to be selected. It's not guaranteed to be selected, but it might be selected with higher probability. Okay? Is it clear now, the algorithm clear? Okay. Type. Let me ask you another question. Okay, let me ask you Yusuf. Okay. Let me ask you a question, Yusuf. If it is guaranteed to select always the best state, will that make it complete? Still, yes, because that will be the standard algorithm, right? Because the standard algorithm will always select the best. Okay, so still this one is incomplete. Still is incomplete because it might go to it might be stuck at a local maximum. Whenever the hill climbing algorithm stucks at a local maximum, then it's incomplete. Whenever it's possible to stuck, it's incomplete. Okay, stuck means it will stop forever at that state. Okay, if that's the case, then it's incomplete, of course, because it's not guaranteed to find a solution. Now, another variant is called first choice hill climbing. In first choice hill climbing, we generate successors randomly until one is generated that is better than the current state. What does that mean? Here we assume that the problem is much larger, so that the successors are really huge number. Yani the successor may be thousands. The successor states may be thousands or millions. So it will take a lot of time to go through all of them and find the best among them. Or find the ones that are better than me, better than the current state. So this variant chooses one, it will choose a random successor, and if that random successor is worse than me, I will choose another random one. If it's better than me, then I will go to it directly without considering the rest of the successors. So do you see the difference between this and the stochastic one? So this is called first choice because the first time I will check a state, a successor state, and found that it is better than the current state, I will go to it. Whether it's the best or not, it won't know. It will just go to one state that is randomly generated among the successors, and it was found to be better than the current state. If it's worse than, of course, the current state, then I will choose another random successor and so on. Let me show you an example first. Let's say that we get back to this, and let's assume that this is, instead of 8 by 8, let's assume that this is million by million, or 100,000 by 100,000. Okay, so the number of successors for every state is really large, very large number of successors. Okay, so instead of computing this H value for every successor state and then selecting the best among them, or considering the best and choosing randomly like the stochastic one, what I will do is to randomly generate a successor. Yeah, let's say مثلا from that state, I will say randomly I will go from this state to that state. Okay, I will choose that. This is a successor, right? Moving that queen from here to there. Now I will check the value of that successor. Is it better than the value of the current state? The value of the current state here is 17. This one is 18. So I will choose another random successor. Let's say now the other one is to move this queen from here to here. Now this, if I moved to that state, the value of that state is better than the value of the current state. So I will choose to go to that next state. So now the new state will be the same, but moving this queen to here. I didn't have to evaluate all the successors before I make any move. Okay? Of course, this will be very good or very efficient in cases where the number of successors is huge. If that's 8, instead of 8 queens, I have million queen or 100,000 queens. Very complex problem with so many successors, so that will be more efficient because I don't have to go through all of them. I can just pick one of them randomly, okay, and evaluate it. If I found that it's better, I will go to it. If not, then I will choose another one randomly. This is called first choice hill climbing. I hope that it is clear now, and the difference between it and the standard and the stochastic is clear. Now the question is that complete? What do you think? Faisal? Yes, it can start at a local maximum, right? I might not find any successor that is better than me, and I will stop at that case, and that might of course be a local maximum. So it is still incomplete. It's not complete. But what is the advantage of this, Faisal? More efficient. You mean easier? It will be more efficient. Yeah, it will take less time. It will be faster if I have large number of successors. Okay, so that's what's good about first choice hill climb. Now the last variant that we will study is called random restart hill climbing. So in this variant, we will first go through one of the variants that we discussed earlier, any of them. Let's say that the standard one. So we'll start randomly, and then we try to find the global maximum, and we might start, of course, at a local maximum. So if we found the global maximum, if we found the solution, we will be done. If we are stuck at a local maximum, then we will restart again with a random initial state. Okay, so we will start from scratch again from a new initial state, because if we start at the same initial state, we might be stuck at the same final state. Okay, so we'll start completely fresh. We start from scratch with a random initial state, and we'll go again through the algorithm. If we found a solution, done. If not, we restart again, and so on until a solution is found. Okay, that's why it's called random restart. Okay, random restart. If we didn't find a solution, we restart again from a random initial state. Okay, طيب, is this complete? Yusuf? So finally we found a complete algorithm. So you think it's complete? Okay, so we will continue doing that. Yes, we will continue doing that until a goal is found, which means a solution is found. So it is guaranteed to find a solution. طيب, what is bad then? So that's much better. That's better than all the previous ones, right? Because it's guaranteed to find a solution. Let me talk to another one. Abdurrahman, thanks, Yusuf. Abdurrahman. Yes, the time. It might take forever. Yeah. But it will find a solution. Okay, so that's a trade-off. Yeah, it's not only burning the CPU, as Yusuf just said. It might take years to find a solution. Okay, so it depends, of course, on the problem. Okay, so this is the trade-off now. It's a complete. It will find a solution because eventually we will. In the worst case is that we will by restarting from a random state, the initial state that random initial state might be a solution. Okay, but who knows how much time we will need to find a solution. So that's the bad thing about it. Okay, with that we are done with hill climbing. Any question about hill climbing before we switch to another method, another completely different method? Yes, Yusuf. Oh, no problem. مش عاجباك يعني ولا؟ ما عندكوش حاجة تانية أحسن شوية؟ ما فيش حاجة أحلى شوية؟ يعني ملحها أقل شوية؟ آه، to, of course, there might be research studies on that, but to my knowledge, no, we will not study more than that on hill climbing. But there are other algorithms, of course, that might be that might be better in some cases and worse in other cases. Okay, you will not find a solution that is always better in everything. And even if you look at the search algorithms that we discussed earlier, you might think that A star is the best, right? And it is the best. But don't forget that to make A star the best, we have to find an admissible and consistent heuristic, and that might not be straightforward, right? And also we need to find that heuristic for every problem, and it's not generic. You cannot just plug it in and it will find a solution for you. It needs some human thinking capacity to find a good heuristic. So every algorithm has pros and cons. Okay, so don't think that hill climbing is always bad. Yeah. Okay, you're welcome. Okay, now let's switch to simulated annealing. Have you heard about the word annealing before somewhere or in other courses? Did you actually study hill climbing? I forgot to ask you before. Did you study hill climbing in any other courses before? Okay, how about annealing? Have you heard about annealing? Not simulated annealing, annealing. No? Okay. Okay, طيب. Let me first explain what I know about annealing. It's a physical concept. So when you, what I know is that when you have a piece of metal and you want to make it harder, one way of doing it, of making it harder, is to heat it with very high temperature, and then lower or decrease the temperature bit by bit. When you decrease the temperature bit by bit, eventually it will be harder. So that's a physical concept. You start with a very high temperature and then you cool it, okay, bit by bit until it reaches, until it will be harder. Yes, Ghanem, do you have a question or answer or what? What I know is that it's called also annealing. I don't know if these are the two different names for the same thing or not. But I know it by the name annealing. It might be. Okay. Yes, it's similar concept. I don't know if it's exactly the same or not, but this concept, I'm not a physician, but this concept I know that it's called annealing. Okay, it's to but the goal is the same like what you said, is to get the molecules closer to each other and stable. Okay, that's what will make the metal harder. Anyway, this is a physical concept. How is that related to local search, or how is it related to AI? Okay, we will actually simulate this process and you will see how. Now imagine that there is a surface, okay, and I am dropping a ping pong ball on that surface. What will happen if I lift the ping pong ball on that surface? What will happen? Of course, by gravity, it will move down until it reaches the bottom of the surface, right? Let's say that the surface is like that. Let's say that the surface is like that. So the ball will move down until maybe it reaches here, and it will stop. Okay, now imagine that this surface is not smooth like that, but it's bumpy. It's bumpy like that. It has some bumps here. What will happen? The ball might stuck at one of these bumps, right? It might stuck at one of these bumps. And maybe instead of going to the bottom, it might maybe stop here. This is local minimum, right? And this is the global minimum. طيب, what can we do so that the ping pong ball will actually reach the bottom of the surface? One way is to shake the surface, so that the ball will get around and cross the bumps and move until it reaches the global minimum, until it reaches the bottom of the surface. That's exactly the idea that we will try to apply here in finding a solution to a problem. So we will imagine the task of getting the ping pong ball into the deepest point, and if we just let the ball roll, it will come to rest at a local minimum. But if we shake the surface, we can bounce the ball out of the local minimum. This is what we just described. Simulated annealing is similar to that process. We will start by shaking hard, and shaking hard here in our context is moving from our state fast. So we will be very energetic at the beginning, okay, because we are shaking hard. That means that the state will move easier and faster, or will change easier and faster. But then gradually we will reduce the intensity of shaking. Okay, so we said that annealing, we heat a lot first in the beginning with very high temperature, and then we start to cool down. Okay, so we'll shake hard in the beginning, the state will change a lot in the beginning, but then gradually over time we will reduce the intensity of shaking, which means that the movements of the state, or the changes of the state, will be less frequent over time. This process, as we will actually say in the next slide, will guarantee us to reach actually a solution. Let's get into more detail into the algorithm. So the main idea is to scale local maximum by allowing downhill moves. What do you mean by downhill moves here? I said that in the beginning we will have very frequent moves, right? Now, if you think about shaking, when you shake the surface, the ping pong ball might not go down, might go up, right? It might happen when we shake, right? But now, because we are maximizing, in the previous algorithms, we always go uphill. We always try to, because we are greedy, right? The hill climbing algorithm is greedy, so it tries to find a good move from what good, of course, locally from my state. So it always go uphill. It will never go downhill. In simulated annealing, because we are shaking, okay, we will allow downhill moves. Type, what is the purpose of allowing downhill moves? We want to go to the top of the hill. The purpose of allowing downhill moves is that might lead us to the top of the hill. It's not always the case, as you saw, of course, and as you know. Optimizing locally is not like optimizing globally. You might be stuck at a local maximum. But if you compromised, if you went through a downhill, if you made some downhill steps, that might lead you eventually to a solution or a global maximum. But the idea of simulated annealing is that we will not allow that very frequently all the time. We will allow that, but this will be less probable, which means will be rarer as time goes on. So as time moves, these downhill steps might be taken, but with less probability over time. So let's go through the pseudocode quickly. The T here is the temperature. That's analogy to the actual annealing, and that temperature is decreasing over time. Okay, as we said, start very high and then decreasing, and it is controlled by this variable, which is, or that function, which is the schedule. Okay, T small is the time, so we'll go through time from 1 to infinity, and for every time stamp, we will get the temperature. Let me change this pen. So from that time stamp, we'll get the temperature. T capital is the temperature, and it is decreasing over time. Okay. Now, if the temperature is 0, then we will return the current state. If not, then we will continue. How will we continue? We will randomly select a successor, and we check the value of that successor. If the value of that successor is higher than the current value, my value, which means that the difference between them, the difference is delta E here, the difference between the values is positive, then I will move to that successor. So that's an uphill move. That's similar to what we do in hill climbing. But what is different from what we do in hill climbing is the next line. That's the whole idea of simulated annealing here in that line. Else means that delta E is 0 or negative. I will move. That means that the next successor, or the next state is a downhill. Okay, I will not go to downhill step for sure, but I will do that with some probability. So that means that I might take it or not. Okay, now this probability is E to the power E, this is the probability, E to the power delta E divided by T. Now, delta E in this case is positive or negative. For that line, delta E is negative, right? Because if it's positive, then we are done. If it's negative, then we go here. So delta E here is negative. So we have something like this now. E to the power negative number, let's say that minus P. P is positive number. Okay, so that's minus P now, it's negative number, slash, or divided by T, which is positive number. T is the temperature. Now, as we move in time, T goes down, right? We said that. So that's controlled by the schedule here. As the time goes, T will be smaller. So T will decrease over time, which means that this part without the minus will increase, right? Because T is in the denominator. Which means that the whole number here with the minus will decrease. Okay, which means that that's the exponent of the E, which means that the probability will decrease as a whole. Okay, and that's what we mentioned earlier, that over time the probability of selecting a downhill step will decrease. Okay, the probability of selecting a downhill step, this is the downhill step, right? this will be selected with probability that will decrease over time. Remember, T is not the time. T capital is the temperature, which is decreasing when time increases. We'll have to stop here because we ran out of time. If you didn't get it, watch the lecture again, and if you still have questions, we will start with that inshallah next time. So I will have to stop here. Talk to you inshallah on Sunday. Assalamu alaikum wa rahmatullahi wa barakatuh.